Good afternoon. You hear from me? Yes. Okay, very good. So let's wait a little bit. We're supposed to have 61. Now we have 41. Okay. So just a warm welcome to week number 4, lecture A. So today we are going to continue to study op amps. Okay. I know that some of you already got enough knowledge about op amp. However, we are going to go a little bit further. Okay, so now you can download a copy of your quiz. Okay, and the deadline for the quiz is midnight today. Okay, all right. So the next lecture time, we are going to walk you through the quiz solutions. Okay, so I'm going to share my screen now. We are going to study the op amps. Okay, so we are now in week number 4. So it's but before that, I'm going to remind you. I'm trying to send everybody this file. I want you to go through this file. This is the basic things you have learned in ENGR 065. So you just go through all of them to see whether you can still capture what you have learned, especially put emphasis on the sinusoids and also going through the RC circuits. I'm not going to have time to go through all these slides. Please just serve it as a review, okay? The problem is somehow, let me do a small experiment. Somehow I failed to upload the file in the cat course. They keep stuck in there. So I'm going to upload this one through here. Let's do an experiment to see whether this is working. It's week 4 in here. Do go through. Yeah, can you please download a copy of through the chat box? Okay, do it, please. Okay, so we are going to go through the op amps today. Yeah, thank you, it's working. I tried to put the cat course, somehow I got stuck always in the middle, cannot upload it for some unknown reason. So we are going to go through the op amps. We review what we learned in the last time. We have 3 important assumptions for the idealized op amp, okay? So it's called idealized op amp. So you have a current come in, I in. See 3 main assumptions, okay? Make an ideal op amp. What are the 3? You have infinite input resistance. This R in is infinite. So this is considered broken. So then this thing becomes 0, right? So the second one is called, this guy is 0. So basically it's a short circuit here, open circuit in here. Okay. When we say this is infinite, we can also say this is very, very large. How large is large? I think it's like a mega ohm level, okay? Mega ohm level, 10 to the power of 6. So that big value, okay? 0 output resistance probably is like a micro ohm level, 10 to the power of -3, okay? So the third one is the open loop gain, this guy. So we are talking about VCVS. How to spell this? Okay, voltage controlled voltage source, voltage controlled voltage source. So it's a dependent source, you have learned. So the size of this voltage in here is proportional to a control. This is it's called control. This is a control. Control voltage controlled voltage source. Okay, so I think this is clear, right? So VCVS. So the no current, so I in is 0. So in other words, if you have a very tiny fluctuations here, then this is going to be infinite. But in physics, you cannot be V out becomes infinite. If that voltage is infinity, what is going to happen? It can get you shocked, you know, and it'll kill you, right? So in reality, you have a VCC, you have a minus VCC. So these are considered as the maximum will get capped, okay? Capped there, okay? So it's also called saturated there. So if this is open loop, just as is in this slide, your output is very easy to get capped value, saturated there at this VCC level or minus VCC level, depending on the polarity of this. So what I'm trying to say is this open loop is actually very sensitive to any type of noise because noise is everywhere, right? So we don't use that. So we use it in what they call feedback setting configuration. So we usually will use a negative feedback to bring it. So one of the ideas is this is what we call what? It's called a voltage follower. Voltage follower. So this V out equals V in. And people may say, oh, why bother we do that? So in the quiz number 2 last week, you want to make 0.5 cascaded with another 0.5, and you want 0.5 times 0.5 is 0.25. In between, you have to put something like this. This is called op amp, so that you have the needed impedance matching. Okay. So because A is very, very big, so this is very, very close to 1. Okay. So that's called a voltage follower. Okay, so we have seen this already, and these are very headache confusion. So we need some basics. Okay, so let's do that. We're going to go very quickly about all these op-amp circuits. So these op-amp circuits are usually very simple configurations. With this as a foundation, you can understand like more complicated cases like active filtering, like integration, differentiation operations. So these are ops, okay, operational. So you make the signal, transform it, operate on it, become another signal, right? So let's start. So inverting amplifier. So this is a typical of inverting amplifier, okay? So let's try to see what's going to happen. So this is called source follower, okay? Source follower. You have seen this already, okay? You have seen this already. So we assume everything we are talking about op-amp here are the ideal op-amp, okay? Ideal op-amp means the current here is 0. No current flow in, okay? Find the gain above circuit. So you will see that has nothing to do with RS, nothing to do with RL, nothing, okay? So what they have is a large input resistance. That means it's open circuit here. So you have open circuit in here. Small output resistance. So you have unit gain here, very close to 1. source follower. So that's exactly nice for our separation between. So like you have a voltage divider in here, you have another voltage divider in here. So you put this one, this circuit in here. So you get 0.5, 0.5 equals 0.25. You need this one. Otherwise, as you show in the you experienced in the quiz number 1 last week, you get 0.20. Okay, surprising. No surprise. So it is commonly used as a buffer between load and the source. The impedance are not well matched. Once you put that for this guy in, then it's matched. Okay, you have worry free.
Sir, I have a question. So it's 0.2 because of the voltage drop, right? And then the OAM takes care of the voltage that will be dropped during the process, right?
I think that we explained here. So you have a resistor. So this is the voltage divider, right? So you have another voltage divider. So this is a 0.5 in the middle. This is a 0.5 in the middle. Okay. So then you connect this one too. So from here to here, this V4 divided by V1 is 0.20, not 0.25, because this is not matched. Okay. Did I answer your question?
Yeah.
Okay. So if you insert the whole thing here, inside here, then it's matched. Then 0.5 times 0.5 is 0.25 instead of 0.20. That's the beauty of last week's quiz. Although very simple, but I hope you will learn the lesson without making that kind of mistake. Don't ignore those load impedance matching issue. Okay. But how to prove it? That's easy. You apply those 3 principles. Okay, 3 principles. So how to prove it? Let's prove it. So I know that assume this is A. Okay, assume this is A. Assume this is epsilon. Okay, epsilon. So the V in minus V out. Okay, so this is also V out, right? V out. So this difference is V in minus V out. Okay, then it times A will equals V out, right? So again, then we can see that V in is V out. Let's say, let's do it. V in is 1 plus A divided by A, V out. Okay. So when A is very, very big, then this term will go to 1. Okay, go to 1. So that's why in and out are the same. So that's why we call it follower, source follower. Okay. So this is called a source follower, the simplest case. But remember, the signal is coming to non-inverting terminal. This is the inverting terminal. What is an inverting op amp? That means, so your signal is getting to the inverting terminal. This is the inverting terminal. And you put non-inverting terminal to ground. So what is the voltage here? What is the VE? Because according to what we have learned, this is infinity gain. So this should be the same as this one. So this can be regarded as a ground. It's almost ground. So that's why I have VE. Do you guys know what is the VE? Have you heard about this? What's E? Type. Nobody type for me. Okay, so this is a ground or earth. Okay, so virtual earth. It's virtual earth. So usually you ground to earth, right? So V is ground. So this is 0 basically. This is 0. This is also 0. Okay, also 0. So at this point, we apply KCL at this point. So V in divided by R is this current, right? Then V out minus V in minus 0, okay? So this is 0, okay? V in minus 0, so V in minus VE, okay? V out minus, so this goes to this way. So this is this direction, minus 0. So these two current convert to the same point. While we don't have, this current is 0, I in is 0. So therefore, anything add in, so it should be 0. So that's the KCL, right? KCL. All right. So we do something. We move this one this side. We have V out divided by V in is this guy. So this is called feedback resistance. This is input resistance. It's minus R1 R divided by R2 divided by R1. So in other words, if I have a voltage here is 2 volt, can I have some voltage here 20 volt? No, 12 volt. Okay. Yes. So that's called amplification. Remember, if you have a voltage divider, is it possible that you have V out greater than the V in? No, it's not possible. It's always less than V in. So you have a 10 watts in here, then this one cannot be greater than 10 watts, cannot amplify, you can attenuate. So that's the beauty, because you can choose arbitrarily the ratio of R1, R2. So that is exactly called amplification, amplifier, if needed. So that's why our voltage divider, you cannot step up the voltage. Okay, if you want to step up, you have to use op amp. Remember, in this type of setting. Okay, but you may say, "Hey, I don't like this. I don't like this negative sign. What are you going to do?" I want to remove this sign. What I'm going to do? Easy. So you construct another one. Okay, so but you put this one arbitrarily R. You put another one arbitrary R. So then you can see from here to here is -1. Okay, is -1. You cascade this guy to this guy. So then this V out new, this V out new versus V, so V out new versus V in, what's this? Did you remove the minus sign? Yeah, you did. All right. This is how we remove this negative sign, okay? So inverting op amp, is this beautiful? Yes, it's very beautiful. But what if I have more than one signal? I have a V in 1, I have a V in 2, I have another signal. So I want to, this one, I want to add into this one, so you can just combine them, solder them together. You will have something, suppose this is a VR3. So you can imagine what are you going to get according to superposition principle, okay? So what are you going to get is a V out equals minus R2 divided by R1. So this is we just learned here, right? We learned here. But you can imagine we have another one is R3, sorry, R2 divided by R3. And V in 2. So then that means we can put two signals adding together according to different coefficients, combine them. is this doing a computation already? Yeah, it's operations. So that's why it's signal adding together. So you have two signals, you want to add them together. You cannot simply sew them together. Then you expect it will add together. That's totally wrong, okay? Don't make that kind of low-level error. People will laugh at you and also me. Say, how come? So you have to use this op amp to be able to add those two signals together, okay? Like this, okay? So, of course, because it's a negative sign, so so the phase is opposite, okay? It's 190 degrees. If you have sinusoid, you have reverse sinusoid. So that is inverting terminal. What about the non-inverting amplifiers? Again, your signal is from here, but remember you put this one into non-inverting terminal. The signal goes to non-inverting. So here signal goes to inverting terminal, okay? Inverting terminal. So we are now doing non-inverting terminal. So then we want to check what is my V out. So here I put a feedback resistance in here. And then we want to check V out divided by V in. What's the gain? What's the gain? Okay. We are talking about a gain, okay? That means amplification coefficient. So here's the reasoning, okay? We know we don't have current going inside here. This is 0, okay? And the difference between this one and this one is this is 0. Okay, there's no difference. It's epsilon. It's almost 0. So in other words, if this is a VRS, this is a VRS. So this is also VRS, right? The same. Okay, VRS. So because this is no current going inside, you can say this is not connected, right? Not drawing anything. So then the whole thing from here to here, what's this? This is a voltage divider, right? So what is the voltage of VRS? VRS is a voltage divider, okay? There's a voltage divider, okay? So it's RS, what's left, then and total R. So from here to here, total R is RF and RS and the V out. So this is a voltage divider, RS, you know it, okay? And remember, we already said that on here, V plus, that means here, this is V plus, equals V in, that's for sure. V in is VRS, okay? So V in is VRS, okay? Because A is infinity, okay? So if this is not almost 0, then you will saturate your output. So that's not possible. We don't do that. So in other words, now we can do this. V out, V in. What is V in? V in is V plus. V plus is this is a V plus. Is also VRS. So V out divided by V in. Okay, divided by V in. So V in, because I in is also 0. So VRS is V in. So this is actually equals also V in. Okay. So we divide, so V in go to this side, this guy go to this side. So it's RS plus RF divided by RS. Then this is 1. This is so this is always greater than 1. So this is always amplifying. Okay, amplifying. So when you do a non-inverting amplifier, it's always amplifying. Okay, it's not possible to do stepping down. So does the R for the input affect anything then? That's a very good question. In fact, theoretically speaking, yes. Okay, it is usually for safety purpose, internal matching purpose. Okay, but for this case, you don't see there's a difference in there. Okay, so good question. The role of R. Okay, role of R. Okay, it is a much deeper question, needs a much deeper analysis. in that case, you have to consider non-ideal for the non-ideal op amp. So in this case, the R in here should be choosing satisfy those non-ideal situations. Okay. Okay. But in ideal case, this R does not play a role here. Okay. It only happened in here. Okay. But I have to tell you, it's not like R, this guy is useless. No, that's not true. Okay. It has its role. But to understand the role, you need to put all the non-ideal factors in and analyze it. There is indeed, in a non-ideal case, there's indeed optimal R, the best R option put there. Okay, that's a much deeper question. Okay, use for cases of electrical blowback there. Yeah, this safety reason is there. Reduce some risk of short circuit. If somebody touched here and ground, at least you have an R in here. Otherwise, you got a very, very big current to burn everything, right? Sort of protection. Good question. I like what you guys asked. So let's move on and showing this case. This case is the one I mentioned in here. So what if you have two sources? You want to add them together. Okay, you have a signal 1, you have signal 2. So S stands for source, but I prefer to call it a signal. Okay. Yes, you have two signals. You want to add them together. Okay. Yes, thank you. So then you apply what? KCL. Okay. So the current coming in here, current coming in here, current coming in here, adding this point. And also you have current here. This is 0 actually. Add all this together and the current will have a balance. The add together is 0. Okay. So this is a KCL. Okay. So adding that one, you will see V out can be expressed as a linear combination of this guy and this guy. Okay. So you have two different gains. Okay. And those gains can be chosen arbitrarily set. Okay, can be larger than 1, can be less than 1. Okay, larger than 1 is called amplification. If less than 1 is called refresh memory, attenuation. Okay. Okay, so of course we can extend this one to n of them, summation. So basically you have n signals, you can summation like this. Okay. All right, so that's called summation amplification. What if I do differential amplifier? Okay, so the reason is I amplify your differences. So you put one in non-inverting terminal, another one in the non-inverting terminal. Again, you put R2 in here to do the ground. Okay, to do the ground. So, and you also have R2 here. So do you see the symmetric manner, R2 here and R2 here? Okay, so how we can derive? So we want to see the difference between V1 and V2. So we can do superposition principle here. So we assume one, this is 0, then only consider V1 first, then see what is the V out due to V1, due to V1. Then we check the V out, V1, set V1 is 0, and V2 is not 0. Then we get a V out due to V2. So then you add these two together when V1 and V2 are not 0. Okay, so that's called superposition principle. So let's short the V2 first. V2 first meaning I set V2 is 0. Okay, when V2 is 0, what's going to happen? because this is 0. So this is 0, meaning it's like ground, okay? So these two together, this is a ground. There's no current in here, so there's no current in here too. So this is also 0, okay? So that's why we can directly write like this. So it's 0. Make sense? But ideally, you should write down something like, this is something like this. You have a R2, you have a R1, then you have the ground. You put this one here. But this is the same as this one because there's no current in here, okay? So we can ignore that. So then, so this is 0, this is also 0. Then this is what we just learned in inverting amplification. So R2 divided R1 is V1, right? So this is V out 1 is called V out 1 is V out due to V1 alone only. Okay. So now we are doing V1 is 0. When it's 0, basically it's like this is everything is 0. Okay. Yeah. And then we have our, so this is just a 0. Okay. This is just a 0. So then we only have V2. Let me see. So we did something differently. Did you see that? So because V1 is 0, so this is negative sign, and I hope you observe we flipped it. We flipped it. So this V2 we apply to here. Okay, we apply to here, and so then this is no current coming in. So what is the voltage in here? So this is the voltage divider, right? So when you apply V2, so you have voltage divider. So there's no current coming in here. So what is the voltage in here? So it's R2 divided by R1 plus 1. R2 divided by R1 plus R2. This is a voltage divider, V2. So that is, we put it here, okay? We put this point is this point, okay? But on the other hand, you have a V1, this is V1, okay? V1 is 0, you put it in the ground. You have R1, R2, but this and this are the same voltage. So I know this voltage, right? Do I know? Yeah. So my V out is like another voltage divider here. So V out 2 equals R2 divided by, so something like this. So V out 2 equals R1 divided by R1 plus R2. And no. V out times, okay? V out times, this is the voltage divider, equals what? Equals this guy, this voltage. This voltage is this voltage. This voltage is this voltage. So this is R2 divided by R1 plus R2 times V2. So that's why, because you have this can cancel out. So the V out 2 equals R2 divided by R1, okay, and times V2, okay, times V2. So I hope you understand that here we used 2 voltage divider, okay. So we use this one first, then do a next one later, and these 2 are the same, okay. By doing that, we can say that one is R2 divided by R1 minus. So then in the end, we have a V out is proportional to the difference of the 2 signals. So that's why it's called differential amplifier, okay? So I don't care how big you are, but I only proportion to your difference, the V2 minus V1. So this is a differential amplifier. The key part is here, you need to set this symmetric, okay? So that's called difference amplifier, okay? Difference amplifier. So if you have like R1, R2, R3, R4, you can derive in a different way, okay? So in general, you can do 2 times of voltage divider. So V out 2. So you should understand V out 1 is the same. You have 1 voltage divider. Second voltage divider is like this. Okay, like this. So you can derive that. You can derive that. So therefore, you have 2 different amplification in here. If they are the same, then it's a differential amplification. If they are not, it is not. Okay. So let's see an example. Okay. So R1, R2 are the same. Okay. R1, R2 are the same. Okay. So we find out the V out if they happen to have some internal signal, they have some internal resistance. They are different. So although these are symmetric already, but because of that, okay, then my differential gain will be changed, and my V out, it is not 0 even when the 2 signal is the same. So it's no longer difference. Okay. So according to the V out derivation in general case. So we are going to put in all these numbers. Then we get something close but different. Okay, different. Okay. So therefore, your internal, if these are go to 0, then will be nice. Okay, will be nice. So that's why we need to consider internal resistance. Okay. All right, we review a little bit ideal characteristic: infinite input impedance, 0 output impedance, infinite output gain. So this is our op-amp idealized model. Okay, so that's what we have learned. Also, we talked about source follower, inverting amplifier, non-inverting amplifier, summation, and difference amplifier or differential amplifier. So instrumentation amplifier. We are going to take a look. Okay. So far, have you noticed that we never in the op-amp used any capacitor and the inductor, right? So all these resistors. We already can do quite a lot of operations. Okay, operations. So it's obviously very useful, right? So we are going to see the instrumentation amplifier, source follower, inverting op-amp. So this is just to refresh your memory. So this is non-inverting amplification. Remember, it's always greater than 1. So then you have a summation. You can do as many as you want, okay, put together. Then you have a differential amplifier or difference amplifier. So if everything is symmetric, then you have a perfect thing here. But if it is not, then you have a general formula like this. So you basically use voltage dividers multiple times plus superposition principle. Okay. So we also went through an example to show that if you have a different signal internal resistance, you are going to make the amplification coefficients different, therefore violating the differential amplification rule. That means when V2 minus V1, V2 equals V1, your VL is supposed to be 0, but it's actually not. Okay. So that's very bad. So how to make sure that we can have adjustment so that the V1, V2 will be able to have idealized small impedance. So did I tell you that the best idea to do is to put, so instead of you just add into this one, you add a staging here. So this is basically say, let's just add a buffer stage in here, right? So this is another op amp, okay? So we add this here, the box like this. So then let's try to analyze this circuit, okay? Analyze this circuit. Of course, here we are still symmetric. Did you see that? Okay. So the difference is we added a buffer stage. Do you see that? So we get a non-inverting amplification with a, so that we have infinite input resistance. Okay. So let's check. Okay. So this looks like quite complicated, but it's actually not. So let's take a look at V1. Okay, V1 goes to VO1, so it goes to VO1. So we assume that because one is positive, one is negative, so we are ideally in the middle. This is the ground, ideally. Okay, ideally. So ideally in the middle, this is the ground. Okay, so we put this one, and O1 and O2 will add. So this is the same. So we don't know what says yet. Okay. So we just link to them. Actually, we know it's R2. It's R2. We write R2 here. So for O1 is, so this is non-inverting terminal. You have signal in here. So this is also V1, right? So this is also, so this is V1. So this is also V1, right? So this V1, okay, so of using a voltage divider, because there's no current from here. So I just do a voltage divider. So the V1 should be written as VO1 times voltage divider, which is Rx divided by 2 divided by Rx divided by 2 plus R1, okay, R1, right? So then you write this is just 2R1 minus divided by X2, you have 1 in here, right? So this is giving you this. Okay. So then you have a second stage. Second stage is VO2 minus VO1. We have derived this one before because these are symmetric, okay? These are symmetric. So then we just insert VO1 in here. Let's check VO2. So V out, so VO2 you should be the same because VO2 is also doing this one, is just opposite, right? So VO2 is is the same formula, okay, by the way. So VO2 is also the same, VO1, because this is exactly the same. So therefore, we are getting something like this, okay, getting something like this. R1 divided by Rx, okay, Rx. So this is called instrumentation amplifier, okay. So we can run a few examples. We have done this thing before. I think we have done this example in our quiz, okay. So yeah, voltage divider. So this is a voltage divider. This is considered as a load. Okay, so the load will affect, this is no longer 0.5 once you turn this load on, okay? But if you have this divider here, follower, so then you have impedance matching. So no matter how big is this one, you will not change, this is 50% of this VG, okay? 0.5 is not going to change, okay? Because from that side, this one is broken, okay? This is infinity, okay? All right, so we're not going to go through this one. And this one is deadening. So that's why you need to learn deadening, but otherwise you cannot do this problem because you have a resistor here, and this is the source. how you can equivalent to this one. So what are you going to do? So you look from this and this one inside. It is always possible you can do source and equivalent, Thevenin equivalent, right? So what do you do? Thevenin equivalence, RTH and VTH, you know it, right? So you just do this short. You short this thing, okay, to see what is the value here. 6 parallel to 4 plus 2, right? Yeah. Is this the one? And VTH is the voltage divider, right? So then once you close that loop, you'll get, this is your value here, RTH, VTH, okay. VTH, RTH. That's your equivalent. So then you can compute the amplification and what's your output, okay? Okay, so closed loop gain, you have RB in here. So this is ground. What is the closed loop gain? So very simple. Let's try, okay? So you have no current in here. So this current and this current will go to 0. Add together is 0, KCL. But what is the voltage in here? Because this is no current in here, so no voltage dropping in here, so this is also 0. So therefore, this is a virtual earth, okay? Virtual earth. So therefore, you have, okay, so these are the reasoning, okay? These are the reasoning. Voltage across the RB is 0, okay, because no current. Voltage at the inverting input is 0. So therefore, A is a minus R2. So this is a, so again, this RB didn't play a role, okay? Didn't play a role in here, okay? However, in non-ideal op-amps, how to choose RB is actually a much deeper question, okay? It's better not to put RB as 0, okay? Okay, so this is a closed loop gain, and so let's check. So you add this V in, your signal input is here, output is here. So then without any doubt, you know, because the voltage difference in here should be almost 0. So this is also V in, okay? So V in and V out should be the same because the current in here is 0. So the V in is out, V out. That's simple. Okay, so things like this can be quickly reasoned from the 3 ideal conditions of op-amps. Okay, so the quiz number 1 is basically asking you to reason that. Okay, please do it carefully. So here we are going to say something that probably you haven't learned. It's called common modes and differential modes. Okay. So ideal differential amplifier is like this. So the difference about it. But in reality, there are many reasons they become not the same. Okay, not the same. So you can understand that. Okay, because you said R1 and R1. You have a 2 R1. You have 2 resistors. But remember, resistor has something like even plus or minus 10% error. So the R is actually in the interval, okay? In the interval. So to find the 2 resistors, they have identically 100% identical value. That chance is very low, okay? So you always have some differences, okay? So in this case, so this is the gain. You set 1 0, another one, the output is due to the V2. Okay, another one is due to V1. So that's, we want to know how bad this is, okay? So there is a performance index of a differential amplifier in terms of the gain when both inputs are identical, when the inputs are equal, out of phase, differential. So we want to introduce that. So ideally, we put a common mode and a differential mode. Differential mode means difference. Common mode is the same. They are the same. So let's specify what is CM and DM, okay? So something like this. Common mode is I have a gain. When you have both inputs are exactly the same, they are the same. There is V in, okay, equals V in, okay? My common mode is written as a gain, okay? This gain is actually is ACM, okay? Common mode gain. And this is V in, okay, V in, okay? V in. So that's called common mode, okay? So in other words, my output due to the V in and writing a common mode amplification. So this is A1 plus A2, A1 plus A2. Okay, you don't have you have the same. Okay, you have same. You add them together. Okay, basically. Differential mode means you have a V2 and a V1 are the same. Okay, but they are opposite sign. Okay, opposite sign. Then also equals V in. Okay, so then we try to say what is my output in this case? Okay, in this case, so that this is written as a differential mode. So you denote this guy as this one. Okay, so basically it's A2 minus A1 divided by 2. The reason we have divided by 2 is because you are the same, but you difference. So the difference between V and minus V is 2V, right? So that's 2V. It's difference. Okay, so in other words, the output, if you write in terms of the difference and the summation of the input, and in terms of differential mode and the common mode, okay, common mode. So what we want to say? We want to say, if this guy is 0, okay, then that's nice, okay? Then it's an ideal differential amplification in this case. So then I put ACM as a denominator, and ADM as a numerator. Then the ratio, actually the ratio ideally is infinity, right? Infinity. If this is called common mode rejection ratio is here. R is rejection and ratio, rejection ratio. So if the CMR, the larger, the better. When you buy a differential amplifier, you should check the CMR. The higher, the more expensive, actually. So of course, ideally, the CMR is infinity. Ideally, this term should be 0, okay? So that's why I'm saying impractical, in a non-ideal op-amps, your CMR is a finite number. Maybe it's 10 to the power of 5, but it's finite number. So therefore, even if you have something is equal, this V2 and V1, they are equal, even if they are equal, okay? then your V out is not 0. Okay, it's not 0. Okay, not 0. So in other words, it's very easy to check. So you have an op amp, you have here, so you have 2 term. You put this 2 to 1, okay? Pull out, you just connect this non-inverting terminal, inverting terminal. Then you see, or do you have output? Do you have output? You should have 0, right? Because this difference is 0, right? Right? If you connect these 2 terminals, then what's the voltage here? Is 0. But unfortunately, your output here in practice may not be 0. It may be a very tiny number. Okay, very tiny number. Okay, so that's because of the CMRR is not infinity. In other words, this guy is not 0. Okay, it's not 0, although very small. So that's kind of non-ideal indicator. CMRR. Okay, wake up. What is CMRR? If you don't know what is CMRR, you are in trouble. You don't know CMRR, then it's basically saying that you do not know op amp. Because CMRR is a bridge between your knowledge and the real world use. In real world use, you should acknowledge the non-ideal situations. Okay, this is the beginning of that non-ideal op amp case. Please remember that. Okay, CMRR. We're not going to go much deeper into this, but in reality, CMRR is a very key parameter of non-ideal op amps. So what we're going to do next is to get started on active filters. Active filters meaning you have low pass, high pass, but you are using capacitors, resistors together with op amps. Okay, although you can do RC network or RL network, RLC network to do filters, but those filters are not called not called, it's called passive, not active. Okay, passive components. Then we are going to talk about differentiation and integration. These are all important, 2 important operations, right? So operations. Again, it's op amp, means operation. So active filters meaning you have impedance, not a resistance anymore. So impedance is the generalization concept of resistance. So we use Z instead of R. While Z, R is resistance, but also R stands for real. They are real numbers. But Z here is a complex number, okay? Complex number. So it's also frequency dependent. Different frequency, omega, you will have different impedance, and so on and so forth. Although it looks very simple, so this is impedance ZF, impedance ZS. So it didn't change much. Okay, it didn't change much. So inverting, non-inverting, we have learned that. So those impedance can be arbitrary, any complex impedance. Okay, complex impedance. So just tell you that don't feel hard. This is simple. The thing is how you can convert resistor, capacitor, and inductor into those impedance. So we are going to take a look. So without this CF, okay, without this CF, we are very happy. We know this is an inverting amplification, right? So, but when I do a parallel connection of CF in here, and the story start to change. Okay, why? Because we have to use the impedance concept. So then this is also impedance, okay, for the ZS. Okay, so ZS in special case can be a resistor, but it can be more complicated. Okay, so you may ask, what if I put a parallel capacitor here, C2? Yeah, you can, but this is our next topic. We don't want to make it too complicated here. Okay, so in this case, I told you ZS is RS, okay, the same. So it's minus ZF divided by ZS. What is ZF? ZF is RF with the impedance due to ZF impact. So this is what is impedance due to CF? Okay, we know that is 1 over j omega CF, right? So if you ask me why this, then I refuse to answer that question, okay? But what if you have a inductor here? So this is actually an inductor L is the ZL is j omega L, okay? J omega L. CF is 1 over j omega C, okay? All right, so that's why I need you to read this PDF. I just shared it with you from a chat box. For those who came in late, please get this file from chat box. I'll fix my link in fix my link in the cat course. Okay. It's very strange. You got the freeze and not moving. So you have this one. So this is everybody knows. So there you have a parallel. So you have Z1 times Z2 divided by Z1 plus Z2, right? So this is sorry, 2. So this is Z1 Z1 parallel with Z2 is this. So Z1 is this guy. Z2 is 1 over this guy. Then this Z1 plus Z2, okay? So I hope you can follow. Then we just multiply j omega CF, both numerator and denominator. We end up with, this is 1 here, then j omega CF CRF. So you have RF left in here, okay? So you're going to see that, so V out minus V. So this minus sign is still here, still here. So this is a ZF minus Z. So this is a ZF. This is my ZF divided by RS, okay? So that's why we have this one, okay? So what does this mean? What does this mean? V out divided by VS equals this one. And you also have a J. How can I know what does this mean? Please read that document I gave you to pick up those frequency response concepts. So that means the ratio. So this is all complex numbers, right? These are complex numbers, are they? Yeah. So this is complex number. This is also a complex number, okay? But if I do magnitude, I just do magnitude, then I'll see the magnitude, right? So then the minus sign doesn't matter anymore. So what I'm going to get is something called RF divided by RS magnitude is still the same. But what is the magnitude in here is 1 plus omega square CF square RF square. Then this one, right? There's a complex number magnitude is like this, right? Imaginary part and real part square, imaginary part square, add together square root. So this will give you this, okay? This give you this. So omega, I'll check what's going on when omega from 0 to infinity, what's going to happen. So my omega is very, very small. So basically it's 0. When omega is 0, it's called DC, okay? Direct current, okay? Listen carefully. So then this is actually very close to direct current, okay? 0.01, and so you keep going, then you will see you come to here. It's like eventually, okay? Eventually. So this is 0. when you no, you don't have 0. When you do the log, so basically this is log 10 omega, log 10 omega, okay? So when your omega is 0, then you'll go to minus infinity, right? So, okay. So, but anyway, this is called when omega is 0, what's left is RF divided by RS, RF and RS, okay? When it's DC, okay? When it's DC. So this is also called DC gain, okay? Direct current again, okay? Direct current again. So this point is, this 10 here is direct current again, okay? Again, they use the dB. I explained dB to you. What is the, because we are talking about signal ratios. So it's a 20 log 10 of this magnitude. So this magnitude is this guy, okay? So then you can see as omega goes to infinity, okay, it goes to infinity, then the whole thing will goes to 0. So as omega goes to infinity, this one will go to 0, right? Go to 0. Okay, go to 0. Go to 0. So that is x-axis is log 10 omega. So this is log scale in x-axis. But in y-axis in here is just amplitude ratio. Okay, we are not using, so it's something like this. However, if I also use 20 log, okay, 20 log. So this 10 will correspond to log 10, 10 is 1. 20 times 1 is 20, so this is 20 dB. So then when you go to 0, then it will go to even minus infinity, go to minus infinity, right? It's a minus infinity. So then you do log log. So this log plot, you are going to see something like this. Something very straight line going down, okay? Which is true. Because when omega is bigger enough, then this 1 can be ignored, right? So then square root becomes 1 over omega times the coefficient. So that's why you have 1 over omega, okay? 1 over omega, you can do log is minus, okay? So this is basically 1 over omega, kind of. So that's a straight line, okay? Straight line. So I'm just using this low pass filter to show you that connect all the concepts. If you feel you have difficulties at this point, that's a very good sign that you need to read all these things I'm trying to ask you to go through. I'm going to run through very quickly about this deck of slides. So in the next 3 minutes, we are going to learn the whole semester you have learned. Okay. So you know this capacitor stuff. Now let's take a look at sinusoids. Okay, this is a sinusoid signal. You have a gain, phase, and frequency or period. And then you have a phase lead lag and lead lag. So for the pure resistance, so we're talking about power versus RMS, peak, and so on and so forth. On the other hand, if I put sinusoid going to a capacitor, the capacitor will do a differentiation of it. So what you are going to do is actually you have a shift by the 90 degrees. So if you have this is a cosine here, do a cosine here, then you end up with cosine plus this one. That means you have phase of the lens. Okay. So phase of the lens. And if you do inductor, you have so this is phase lead or phase of the lens. Okay. So then you have same thing for inductor. You have phase lag. Okay, current will lag the voltage. Okay. So you have magnitude and phase of a signal. Okay, phasors and complex numbers. Then any of the complex number, you know this one, do you? This is called Euler's formula. Do you know that how to compute this one? Square root of -1 to the power of square root of -1. Can you do that? If you feel this is something wrong, you never thought about how this is possible, that means you need to go back and visit your complex numbers. So I'm going to speed around the circuit theory, yeah. But I think this part probably impedance, talking about capacitor, inductor. So that's why we have 1 over j omega c and j omega l, you know. Okay, so because you do a differentiation. So how to derive? Why this is true? So this is a derivation, right? So I don't want to insult you further. You have to read it to yourself, okay? And yeah, I'm going to admittance, impedance, high pass, low pass of this RC circuits. So they have worked out examples for you. I think these parts are very simple. Let me see. Yeah, this is the one. We start to talk about the low pass filter. Low pass filter. They're talking about what is the cutoff frequency. Cutoff frequency is when the magnitude is this one. Okay. So you can see my signal is in good shape, but suddenly I going down and it get lost. So it's called low pass, high didn't pass. Okay. But where we draw a line saying that it is actually there's a draw a line in here. So this is omega 0. It's called my cutoff frequency. Where draw the line? The line they said, oh yeah, I need a magic number is 0.707. Remember, square root of 2 is square root of 2 divided by 2 is this one. Okay. But why is strange this thing? So you say, oh, it's 0.070 is roughly here. Yeah, why? It's hard to remember, right? So, but it's much easier to remember. This is called signal magnitude. But what about the power ratio? So this is a signal ratio of amplitude. Power ratio is what? If you drop your power to 50%, then we consider you stopped. Okay. Okay, well, let's stop at here. And remember why where we draw the line. The line is when the power will drop 50%. Power drop 50%, then the signal will drop square root of that because power is signal square proportional. So that's why we have this one. Okay, I hope every dots start to connect and go and review all the deck of the slides. Okay, it's not much, just like how many slides? Only 65 slides to flash review those contents. Okay, so questions? We are going to continue to do active filtering next time. And quiz this Friday's quiz is a little bit involved. So yeah, but today's quiz you should be able to do it using the 3 ideal conditions. You can reason it. Okay. So I got 49 students in my class. I'm going to take a picture of this one. So please try to attend the class. Okay. Any urgent question? Type in the chat. Otherwise, I'm going to finish today's lecture. OOF to the guy who just left. Okay, sorry. No, it's okay. It's okay. Bye-bye. See you Friday. Okay. Oh, maybe tonight. Okay. Bye-bye.